Okay, guys, we're back to start section 10.2. In section 10.2, they are going to review some of the exponent rules that we went over in the first video. So I posted this to your Blackboard under content. This was the intro notes for 10.2. So some of this is going to be familiar with our exponent review from the last video. But in section 10.2, you will learn what I mentioned before, the connection between a fraction exponent and a radical. Okay, so this kind of reviews the product rule and the power rule for exponents. You know, it's the key is when the exponent is on the outside is when you multiply. So there's some extra examples of that. There's also some examples of working with fractions to an exponent. We know to distribute the exponent, and we know to subtract exponents when we have a quotient. Okay, we know we can't leave variables with negative exponents, so we have to move them, right? So this is really the new rule you learn in 10.2 right here. This is a fraction exponent. Anytime you have a fraction exponent, you can rewrite that term as a radical. So it's going to be important to know what form you want your final answer in. If the problem starts off in an exponent form, then you should finish it that way. If it starts off in radical, then you should finish it that way. Only sometimes do you have to start in one version and transfer to another. That only comes up occasionally. So we need to know how to work with both. Whenever I have a fraction exponent, the denominator is going to become the type of radical, and the numerator is going to stay on the inside with the base. So sometimes I like to say, you know, always remember it's that bottom number that is the type of radical. Okay? So you have to rewrite sometimes. So you can use a radical to rewrite each expression. 8 to the 2/3 becomes the cube root of 8 squared. 9 to the 1/4 power becomes the 4th root of 9 to the 1st power. And if you remember from the first video, we had 36 to the 1/2 power, and we know that that's the same as the square root of 36. So we know that's 6. And then we also learned in the first video, this may jog your memory, we had 27 to the 1/3 power. And we know that that is the same as the cube root of 27. And we know the cube root of 27 is 3. Okay? So that's why we have to know how to work with radicals in 10.1 and how to work with exponent rules, because there's a connection between the two. Okay? So I also posted a couple intro examples for 10.2, but we're actually going to do some more today together in this video. So this is also posted on Blackboard right now. It reviews the rule with you, and it even gives you a practice problem to rewrite as a radical. There's nothing I can do with this. This is considered done. Because this is the 15th root, it means that I have to have 15 of the same thing in order to come outside of the radical, and I only have 11. So this one's done. So here is an example of using both forms in the same problem, because you start off with a fraction exponent and an exponent rule. So we know we have to multiply that. Multiply straight across, 8 to the 2/3 power. And the only way for me to see if I can break this down and evaluate it further is to rewrite it as a radical. So I know that's the same thing as the cube root, because the 3 is on bottom. The cube root of 8 squared. Well, what is 8 squared? 64. Now, a lot of times people will leave it written like 8 times 8 because we know that when we have a radical, our next step is to try to break it down. That's what we learned in 10.1, is how to take a radical and break it down. 64 is the same thing as 8 times 8. So when I start my factor tree, I remember that the cube root of 8 is 2, because you can get 3 2's from each of these 8's. So each group of 3 is represented once when you bring it outside the radical. So this group comes out, represent itself once. 2 times 2 is 4 is actually the answer. Okay? So a lot of times we do have to rewrite something from exponential to radical form in order to simplify further. This was just an extra example to remind you that this 3 has to be distributed to both of those items. I did not even realize this was on here. Must have been a question in class that day. But hopefully you know to distribute that exponent. 8 to the third, you can figure that out in your calculator. 8 times 8 is 64 times 8 again, to simplify further. But this is an intro to the rational exponents. Now we're going to do some examples together, about 5 examples together, and it'll finish our instruction for 10.2. Before I do those 5 examples, I almost forgot that I am going to be scanning this and putting this on Blackboard for you guys. I wanted to tell you, this is some more practice problems for 10.2. And you can see I've worked out some of them and shown some work in some cases on the first row of problems. And I'm actually starting with this example today in notes. You can't see it very well because this is a print document. But just to let you know, I am posting this on content. So please see if you understand how I got these answers to these questions. And then remember that you're free to do any of these problems when I post them because there's answers at the bottom for you. So, almost forgot to mention this because we're picking up with this problem together. So this will be scanned and put on Blackboard as soon as I finish this video. Okay, so that particular example that I want to do is 81 to the 3/4 power. So I know that I have to rewrite this as a radical. So that's going to be the same as the 4th root of 81 to the 3rd. Okay? I also know that I'm going to have to break this radical down. So instead of putting 81 to the 3rd in my calculator, which would give you 531,441, that's just going to be a big number. I know that 81 to the 3rd is the same as 81 times 81 times 81. Does everybody kind of get where I'm going with this? Because I've got to break it down. At the end of the day, I want to know if there are any groups of 4. I know I have 3 81s, but I need groups of 4 in order to break this radical down. So let's see if I can get any groups of 4. I know that 81 is 9 times 9, and that breaks down to be 3 times 3 and 3 times 3. So then that kind of shows me that I do have a group of 4 right there. I'll try to show up just a little bit more. So I have this group of 4 3s. Well, I need a group of 4 in order to come outside of the radical. So I know that this group of 4 3s, is going to be able to come out of the radical. But when it comes out, I only represent it with 1 3. Well, isn't the same thing going to happen for this 81 and this 81? This is the same. 9 times 9. 3 times 3. 3 times 3. So that's also going to be a pair that I can represent with 1, because it's also going to come outside of the radical. And then you can definitely understand that this will produce the same 4 3s. So this will be another 3 that gets to come outside the radical. There's nothing left inside. If you were to put in your calculator 3 times 3 times 3 times 3 times 3 times 3 and keep going, and through these 3s as well, you would get 531,441, which is what 81 to the 3rd is. So there's no radical left. This is the same as 3 to the 3rd power, which is 27. And that's the answer to that problem. Okay? Sometimes people explain this in an alternate way. So some people get it really well this way. I also want to point out to you that I could have had this 81 in parentheses. So some people understand it to be this. So whichever, and if this helps you, then do it this way. Some people say, well, what is the 4th root of 81? By itself, not 81 to the 3rd. And whatever the 4th root of 81 is, I'm going to raise that to the 3rd power. Well, if you look at this, the 4th root of 81, we know that that's 3, because 81 is going to give us those 4 3s. So that's the same thing as saying 3. The cube root of 81 is 3 to the 3rd, which is 27. Okay? So there's 2 different ways to do it. No matter what, you need to have some knowledge of these factor trees, so that you can handle these roots that are bigger than square roots, cube roots, 4th roots, and all that. You need to understand that you're looking for groups of numbers, but all of that depends on whatever number is in the radical here. Okay? All right, so let's keep going with some examples. All right, let's throw in a negative exponent. So what if we had 27 to the negative 2/3 power. Well, think about what we know about negative exponents. You can't leave them negative, right? So how do I make it positive? Right now, it's all over 1. So if I want to make it positive, then I need to move it down. So it's going to be 1 over 27 to the 2/3 power. Right? Well, I've got to figure out how to handle 27 to the 2/3 power. I know it's under 1 and all, but I still need to know how to handle it. So let's rewrite it. That's the cube root of 27 squared. Right? Cube root of 27 squared. So I can leave it this way and do 27 times 27. Break that down. I know that this is 9 times 3 is 27. So that's going to give me my 3 3s right here that will come outside. This one will produce the same thing. So it's looking to me like it's going to be 3 times 3, which is 9. Those of you that like the alternate way that I just showed you a minute ago, I could do the cube root of 27 squared, and I know that the cube root of 27 is 3. Right? So that would be the same as 3 squared, which is 9 again. So the cube root of 27 squared is 9, but in this problem it was 1 over that. So this answer is going to be 1/9. Okay? All right. We're going to do one more like this, and I'm only going to show it this shortcut way right here. Okay? Just to save time. So 8 to the negative 4/3. So it's a negative exponent, so I know I need to move it down. So 1 over 8 to the 4/3 power. And then I got to deal with this 8 to the 4/3. So let's come over here. So 8 to the 4/3 power is the same as the cube root of 8, right? 4 times. Agree? Well, what is the cube root of 8? The cube root of 8 is 2. So 2 to the 4th is 16. So this is going to be 1 over 16. Okay? You can also see that because if I broke this down, we know that 8 breaks down to 2 times 2 times 2. So we can see all those pairs coming out. So that's another reason I did not do the factor tree for this one, since it's just 8. All right. Well, there's a couple more examples that I want to talk to you about because this is when we kind of use our knowledge of fraction exponents. And we combine that with how important the base is. Because sometimes the problem will try to trick you into thinking there's more that you can do to simplify. You can only simplify the most if you have the same base in the whole problem. If there's any differences in bases, the number like under the exponent, then you know there's going to be not as much that you can do. Okay, so I'm having trouble with my example. All right, so m to the 5/3 power times m to the negative 1/3 power. So they have the same base. So I know I'm going to be able to do some stuff. Well, we have exponents, but they're not outside of parentheses. So what does that mean I do with them? It means I'm going to add them. And I'm glad that they have the same denominator already, because that's going to be less work. Plus a negative 1/3. 5/3 plus a negative, that just becomes 5/3 minus 1/3, right? So that's going to be 4/3. So then I know my answer here is going to be m to the 4/3 power. This is what we're going to call exponential form. Because I'm leaving my final answer with an exponent. If for some reason the instructions wanted your answer in radical form, I've got more work to do, because that means I'm going to have to convert this to be the cube root of m to the 4th. And when I look at it that way, when I look at it in radical form, there's more that I can do. But I don't know that if I leave it in exponential form. So you really need to know what form your final answer needs to be, based on the instructions that whatever they're provided. I know that this is 4 m's, and I need a group of 3 to come out. So these 3 m's are going to come outside. They're going to get represented once. And then this is the cube root, and there's 1 m left over. So this would be your final answer in radical form. Okay? All right, I've got 3 more to do with you. So let's look at the next one. Let's say I have x to the 1/4 power times x to the 2/3 power, and all of that is raised to the 3rd power. Well, there are some choices here because they have the same base. So whenever you have the same base in a problem, which here is just x, no other bases, I probably have some variety as to what I can do first. Some of you may have looked at this problem and the first thing you thought about was multiplying the 3 into both of those. That would be okay. Others of you might have looked at this and said, well, these have the same base, and I'll do parentheses first, and I can add these because they have the same base. So either way is fine. I'm going to follow order of operations. Please excuse my dear Aunt Sally. So that means what's in the parentheses first. But you should get the same answer in this particular case if you were to distribute the 3. So same base. So I'm going to add the exponents. 1/4 plus 2/3. I know that I'm going to have to get a common denominator, right? Which is going to be 12. So it's this times 3 and this times 4. 3/12 plus 8/12. It's going to give me 11/12. Agree? So now I can write this problem to be x to the 11/12 raised to the 3rd power. And I'm going to come down here because I've got some more work to do. So now I'm going to distribute this 3 in here because it's 3/1, which is multiplication straight across. So that's going to give me x to the 33 over 12. Well, if you left it in exponent form, you might think you're done. But I know that I have groups of 12 inside of 33. So that means if I was to rewrite this, it would be the 12th root of x to the 33. 12 goes into 33 2 times, right? So 2 x's get to come out. It's still the 12th root. 24. 12 times 2 is 24. 33 minus 24 is 9. So I know that there are 9 left over. Everybody see that? Well, guess what? There is another skill that happens every once in a while. This is an example of a radical that can be reduced. I wonder if you can see why. If I rewrote this, wouldn't this be x to the 9/12? And I know that 9/12 can be reduced. So isn't it the same as 3/4? That would be a yes. You can reduce radicals just like you can reduce fractions, different kinds of radicals, if both of these numbers are divisible by the same thing, same number. Both of these numbers are divisible by 3. So 12 divided by 3 is 4, 9 divided by 3 is 3. Since they're both divisible by the same number, that's what allows me to be able to write this as x squared onto the 4th root of x to the 3rd. And this would be your final answer in radical form. That's supposed to be right beside each other. Just kind of looks weird. If they allow you to leave it in exponential form, you could have stopped here. Some people might have noticed from the very beginning here that this fraction could be reduced. Both of these numbers happen to be divisible by 3. So right at this point, some of you may have also said, well, this is actually the same as 11 over 4. And then I know that 4 goes into 11 2 times with 3 left over. So that's why you see this 2 times and this 3 left over. So it just depends on when you notice that you need to reduce. You can reduce it as a fraction in the exponent first, or you can reduce the radical itself. Okay? Alright. And I will post these examples that we do together as well on Blackboard under content. So I want to look at one that doesn't have the same base, and then I'm going to look at one more that does have the same base, but it has a lot of steps. So 2 more. I think this is the longest section if you want the truth. Adding and subtracting radicals also takes a while, but we get to that later. 81 to the 1/4 power times x to the 2/3 power, all of that to the 3rd power. Well, this is a little different. I don't have choices as to where I can start on this problem because I don't have the same base on the inside. Different bases. So since I have different bases, I can't add those exponents. So I can't add those exponents. So I have no choice on this problem. I've got to distribute this 3 into the problem. All right, so that's going to give me 81 to the 3/4 power. And we've already done that earlier today in an example. So that's going to help us out. And this is going to be x to the 2nd power, because it's going to be 6/3. Remember, 3/1 multiply straight across. So this is 81 to the 3/4 times x squared, right? And we know from an earlier problem today that 81 to the 3/4 is the same as 27. So the answer to this is 27x squared. Okay. I'm going to draw an arrow here so that you remember we did this in an earlier example. Because it definitely is the 4th root of 81 to the 3rd power, right? But we know that that's equal to 27. Okay? But I just wanted to show you this because they have different bases. So I'm never going to add exponents in that problem. All right, last example. This one takes a minute because they all have the same base. There's more we can do when they have the same base. So we have, for our last example, a to the 3/4 power times a to the negative 1/2 power all over a to the 4/3 power. So because we have the same base, there's a lot of different places we could start. Some of you at the top see that you can add those exponents. You could add those because they have the same base. Some of you don't want to make this positive, are used to making your exponents positive first. So some of you may have thought about bringing this down to the bottom to make the 1/2 positive. If you bring that down to the bottom, you'll have to get a common denominator down here because you'll be adding those exponents. So either way, you're going to have to get a common denominator. To reiterate our negative exponent rule, I'm going to do what I just said first. I am going to drop this term down so that I can take care of that negative exponent. So that's going to give me a to the 3/4 on top. Leave it there by itself. And then on the bottom, I'm going to have a to the 4/3 times a to the 1/2. So now I can add those exponents, 4/3 plus 1/2. I need a common denominator, so times 2 and times 3 here. 6 will be my common denominator, right? So that's going to give me 8/6 plus 3/6, which is 11/6. So now I have a to the 3/4 on top and a to the 11/6 on bottom, right? So this is one problem that makes you have to subtract fractions. You know, this exponent down here is, this fraction is definitely larger than this fraction. The reason why I'm looking at that is because some of you know that when you subtract exponents, you put your leftovers wherever the higher exponent is. Well, I know 11/6 is higher than 3/4 because 11/6 is improper. So it's got a hole in there. It's 1 5/6. So I know that my final answer is going to have my a's in the bottom. But I'm just going to subtract them the way they are, top minus bottom, to reiterate that fraction rule. 3/4 minus 11/6. So now I need a common denominator again. So let's do 12. So 4 times 3 and 6 times 2. So that's going to be 9/12 minus 22/12. And you can see there that I'm going to get a negative number. 9 minus 22 is negative 13. So this is what's left over, but I know that it's not going to be negative because I'm going to put it in the bottom where the larger fraction exponent is. So 1/a to the 13/12 would be the final answer to that question. I'm going to leave it in exponent form because it started out with exponents. So I'm going to leave it like that. And also the reason I'm leaving it like that is because you'll learn later on in this chapter that we can't leave radicals in the denominator of a fraction. So if I was to rewrite that, it would put a radical in the denominator, and that's illegal in math. So this is more for the lab, this last example, to be honest with you, but it's important that you know all those rules for exponents, even when they're fractions. Alright guys, so this is the end of the video for 10.2. I'm going to be posting some documents that we did today, and I'm also going to post some documents for the next couple lessons. Alright, we'll see you for 10.3. Y'all have a good one.